Okay, so here's another set of equations since we're just getting started with our shear force and bending moment equations, or diagrams. Let's look at this one. This is a simple supported beam with a load P right in the middle. Now, if we were to write equations for this, how many sets of equations would we write? We'd have to write 2. They would not be hard, but it would take quite a bit of, not quite a bit, it would take some effort. You'll find out as we go through this, you'll be able to get these very quickly. Again, I'm going to shortcut the process a little bit by telling you that the reaction here is P over 2 and the reaction here is P over 2. So drawing our shear diagram, remember we're using the relationships that the change in shear is the area under the load curve and that the slope of the shear diagram is equal to the load. Now what kind of shear is that on the left side? Positive or negative? Positive. So I'm going to start at P over 2. What kind of shear is this on the right hand side? Negative. So I should end at negative P over 2. So there's my starting points. According to this, the change in shear between any 2 points is the area of the load curve. So let's look at the change in shear from 0 to L over 2. What's the load curve there? 0. So there's no change. So I should stay at P over 2. And what curve should connect those lines? Well, according to this relationship, it should be equal to the value of the load. The load is 0, so that means the slope is 0. Now what happens as I go from the left side to the right side and I pass them this load P? How much is my shear change? Negative P. So I should go down to minus P over 2. What's the change in shear between L over 2 and L? Well, it's the area of that curve. What's the area of this part of the curve? 0. No change. So I stay negative P over 2. That's good. I match my endpoint. And the slope of the shear diagram should be given by the load, and the load is 0. So 0 slope. So there's my shear diagram. Now let's do the moment. What's the moment here? What's the moment at a pin? 0. What's the moment at this pin? 0. According to my relationships, the change in moment between any 2 points is the area under the shear diagram. And then the shape of the shear diagram, its slope, is given by the shear. So let's look at this part of the curve. That's the area of the shear diagram. What is the area of this part of the shear diagram? Looks like it's the length of L over 2 times P over 2. That's PL over 4. And it's causative. So if I start at 0 and add that to it, I get PL over 4. What's the shape of the curve in between? According to this, it's equal to the shear, and the shear is constant and positive. So again, if I look at this, I should see that I have a slope of P over 2. What's the change in moment from L over 2 to L? Well, go and get the area under the shear curve from L over 2 to L. And that'd be minus P over 2 times L over 2. And if I add that to PL over 4, I get 0. Great. And the slope of my curve is equal to the shear, and the shear is constant and negative, so I have a constant negative slope. In this case, it's minus P over 2. And there is my moment diagram. So where's my maximum moment? At L over 2, and what's the value? PL over 4. Even if you had written the moment equations, you didn't have to go back and evaluate the equations to find out where they had a maximum value. This graphically just shows you that. What time is it? I think we'll stop here. I won't have time to finish it. I'll come back to this one on Tuesday. So let me stop this.
So, Mohammed, we have some lunch.